I want to cover chapter 3 called Decision Analysis. And we're going to talk about using decision tables versus decision trees. So I'm going to cover the first part of the chapter. And here we list the steps of decision-making process, describe types of decision-making environments, make decisions under uncertainty, and make probability values to make decisions under risk. And we'll talk about the difference between uncertainty and risk. We're not going to do trees, we're not going to do the Bayesian analysis, but we will use the QM system to solve problems, and I'll probably post a separate video on that. So let's get into it. So we're going to cover the first 5 sections, basically. So what's involved in a good decision? A good decision results in a good result, basically. There's all kinds of decision-making methods if you don't know what to do. If you can reduce everything to a yes-no question, you can use a sophisticated decision-making tool called a coin. Heads are yes, tails are no. You can make lots of decisions in a short period of time. The accuracy and validity of those decisions, though, are suspect because basically you're guessing and you're using chance to make the decision. So decision theory is a way of looking at breaking down maybe a complex decision between alternatives. I mean, if we look at one alternative, one case where would you like $100 or a slap in the face, it's a pretty easy decision. Most people will take the $100. There might be a few that prefer the slap in the face, but that's a topic for a psychology class. Now, if you look at two good decisions, you get into college A and you get into college B and you like them both, how do you make that decision? That's a little bit tougher to do because they're both positive results and you kind of agonize over those. So a decision table is a way to perhaps put some numbers around it and scope the problem and provide a basis that you can look at analytically to help you decide. I wouldn't necessarily go with the analytic decision, but let's take the example of the college. You might look at locations, you might look at size of school, programs offered, quality of the athletic program might be a factor. Prestige, reputation, all those things are factors. If you weigh them all plus and minus and add them up, the one that are more positive might be the choice you should rationally go with. When you do something like that, an interesting thing happens. If you reveal your emotional choice as well. What am I saying? Well, let's say you add it up and you decide college B is the place you want to go, or you should go rationally. And if you go, yes, because that means that's what you also emotionally want to do. If you're slightly disappointed by that, your emotional choice was obviously college A, and you're still conflicted a little bit. So I think some sort of decision-making approach is good because it gives you some rational basis for making a decision, and it also reveals your emotional choice sometimes. I don't think that's universal. It may only apply to me, as a matter of fact. So a good decision is one that's based on logic, considers all available data and alternatives. One thing they don't talk about here is gut feeling. So here's a 6-step in decision making. And every chapter in this book has a 6-step, 7-step, 8-step, 4-step method for whatever it is they're doing. And they all start clearly with the first step here. Clearly define the problem at hand. If you don't clearly define the problem, you're going to have a hard time with the rest of this. List the possible alternatives, identify the possible outcomes or states of nature, and we'll talk about what that is. List the payoff, which is usually some sort of money or cost. You'd want to maximize money, you'd want to minimize cost. For each combination and alternatives of outcomes, select one of the mathematical decision theory models, apply the model see what the model suggests your decision should be, decide if you want to go with that decision. So here's this Thompson Lumber company. The company is considering expanding manufacturing and marketing a new product, backyard storage sheds. Their alternatives are to construct a large new plant, a small new plant, do not develop the new product line at all. And identify, the possible outcomes, the states of nature was the market is favorable or the market is unfavorable. Right now we're teetering on a time where people are postulating or guessing that there might be a recession coming. So this would be the kind of decision you want to make. Do we expand our factory if a recession is looming, or do we not expand our factory and wait until to see what happens to the economy? List the payoffs. So you want to talk about what are the conditional values, what are the possible profits for a large plant, small plant, and not doing anything at all, which is always one of the alternatives, not doing anything at all, for the two possible market conditions. Select the decision model. This depends on the environment and the amount of risk and uncertainty, and apply the model to the data. Solution and analysis are then used to aid in decision making. So here's the decision table. You always have the alternatives in the vertical on the left-hand side. You have your states of nature on the horizontal on the top side here. So states of nature, favorable market, unfavorable market. Construct a large plant, construct a small plant, do nothing. Obviously, if you do nothing, the payoff in either case is zero. But if you create a large plant in a favorable market, you could get $200,000 in profit. If you construct a small plant, presumably half the size of the large plant, you would reap $100,000. Now, if the market goes south, you would lose $180,000 constructing a large plant, and you would only lose $20,000 if you constructed a small plant. So this is the way you set something like that up. So decision makers under certainty. The decision maker knows with certainty the consequences of every alternative or decision. Well, that's the case here, because if we look here, we have bona fide numbers and no probabilities. So how often do we know everything with certainty? That's a debatable thing. Decision making under uncertainty, which means we don't know the probabilities, which is probably the most realistic sense of is it going to be a favorable market or an unfavorable market. Decision making under risk is when you know the probabilities. Who knows actually if it's going to be a favorable or unfavorable market? So really, I think most decisions are done under a type 2 scenario, but it really depends on your guesstimation and how you want to structure the model. So there's several criteria we're going to look at, and the names are a little confusing. Maximax, Maximin. The Maximax is a very optimistic decision. The pessimistic one is Maximin. We have this criterion of realism, which I guess was developed by some guy named Hurwicz. Equally likely is by Laplace. And I think Laplace is just a specific application of the Hurwicz model. So 3 and 4 are really the same. And then we have this thing called Minimax Regret, which is a little bit convoluted. So really 1 through 4 are the most important. And I really think it's just 1 through 3, but we will cover Minimax Regret. Maximax. This is what a risk taker will do. He looks at all the numbers here and picks the biggest payoff and says, let's do that. I want to make the most money. So in each row, you take the max. So the max between 200 and minus 180 is 200. We have 100 and minus 20. The max there is 100. And then you take the max of 0 and 0 is 0. And then you take the max of the max. So you get 200. So really it says maxi-max, but it means that you're picking the largest number on the table. And you're going with that. And that's what risk takers do. The risk taker says, oh, I have a chance I can bet $1,000 for a chance to win $2 million. Doesn't think about losing 1,000, thinks about making $2 million and just says, yeah, let's go for it. I have a chance to win $2 million. I want it. On the other hand, the Maximin is the opposite. It's the risk-averse person. You pick the minimum number on a table. Well, what's the minimum number here? It's a 0. That's what I want to do. So you pick the minimum in each row, minus 180, minus 20, minus 0, and you pick the maximum of those minimums. Well, the least everything else is a loss. At least 0 is break even. I haven't lost or gained anything. I'm going to pick that. So the risk-averse person is going to do nothing. They look at this. They don't look at how much you can make. They look at how much you can lose. Well, I can lose $180,000. I'm not doing that. Ooh, I could lose $20,000. I'm not doing that. I don't lose anything with this choice. I'll pick that choice. Okay, so it's Maximin. You pick the minimum of each row, and then you pick the maximum of the loss. So you take the alternative with the least possible loss, which in this case is 0. The Hurwicz thing is a weighted average compromise. It's basically saying if in a state of nature, we have, if there's 2 states of nature, we're picking some probabilities for each state of nature. In this case, when there's only 2, you use their complementary probabilities. You pick an alpha between 0 and 1, which is also a percentage. And when you do that, you then take a weighted average of the maximum in a row and a minimum in a row. And then you end up with a result, and you take the maximum of those results. So if I'm using an alpha of 0.8, that's 80%. 1 minus that is 20%. So in each row, I'm going to multiply 200,000, like in the first row, by 0.8 or 80%. I'm going to add to that 0.20 or 20% times minus 180. When I do that math, I get 124. I do the same thing here. I have 100,000, I have minus 20. I multiply this by 0.8. I multiply this by 0.2. I add them together, I get 76. And obviously when the 2 numbers are 0, whatever I multiply them by and add together is going to come out 0. Then I pick the max of that. So in this case, it would say make a large plant. Construct a large plant. The Laplace considers equally likely alternative for each case. So in this case, when it says equally likely, just take the average. Basically, it's the alpha is 0.5 here. 0.5 times this, 0.5 times that. It's the same thing as adding the 2 numbers and dividing by 2 is equally likely. So I add this, I get 300. So what's the average of this? I add this and I add this and I get 20,000. I divide by 2, I get 10. I add these 2, I get 80,000. I divide by 2, I get 40. When it's 0, 0, of course I'm going to get the average is going to be 0. So here I pick the max again, and really in this case I construct a small plant. Minimax Regret is called opportunity loss or regret. My view of decision making sometimes is if you make the decision model too convoluted, people can't follow it, and therefore you have an advantage in the presentation. Oh, you don't understand this? You don't get it? You don't see what I'm doing? Try to keep up. Try to understand. Let me explain it one more time for you, and you can get people to basically shut up and follow your decision. So here's what happens. The difference between optimal profit and actual payoff for a decision. Create an opportunity loss table by determining the opportunity loss from not choosing the best alternative. So you pick the other alternative, and then you see the difference. Opportunity loss is calculated by subtracting each payoff in the column from the best payoff in the column, finding a maximum opportunity loss for each alternative, and pick the alternative with the minimum number. What? See how I can lose you very quickly by explaining it very clearly? And I don't like convoluted decision making, but you get what we're talking about here. And you can make it more complicated than this. I don't believe in complicated decision making models unless the decision being made is really complicated. If it convolutes the decision, I'm basically not for it. All right, so here we go. Here's the same Thompson Lumber table. So the best in a favorable market is to pick the large factory. So we're going to subtract 200 minus 200. I want to subtract 200. I want to subtract the small plant alternative 100, and we'll do nothing. I'm going to subtract 0. In the unfavorable market, the best alternative is 0. So I'm going to subtract everything from 0. And I think I'm going to pick the minimum, I think, of those. So here's my opportunity loss table. Construct a large plant, a favorable market is 0, unfavorable market is 180. Construct a small plant, the opportunity loss is 120. Do nothing, it's 200 and 0. You pick the max in each row, and you pick the minimum of those maxes, which is construct a small plant. Now, you followed this, hopefully. Let me tell you, I've built warehouses throughout all of Latin America for Colgate-Palmolive. Probably 17 warehouses, either refurbed, remodeled, or built from scratch. In each case, we had the same problem. Construct a large warehouse, construct a warehouse that will cover our needs for 5 years as opposed to 10 years, and do nothing. Do nothing was an alternative because our warehouses were all too small and poorly designed and poorly laid out. So we had to really go through and revamp the entire network. In most cases, you don't build a warehouse to cover yourself for 10 years. You don't build a church for Easter Sunday. You build it for most Sundays, and you burst at the seams on Easter Sunday. When we're talking warehouses, we almost in every case we built a warehouse for a 3 to 5 year span, but in every case that we had, we provided enough land and had a plan B to expand the warehouse when needed. So most of the time we took this middle road, and I kind of think we used a Minimax Regret decision making in the background, and we didn't formally do it. Most of the time we were limited by our capital budget and really stingy finance people, which made the middle road there of constructing a small plant with a contingency plan for expansion what we did everywhere. So this is not an unreasonable scenario that we used here. So now decision making under risk. Under risk, you know the probabilities. Or you think you know the probabilities, or you're guessing what the probabilities are. So you have several states of nature, and you have a probability with each state of nature, and it's called expected monetary value. You take in each row the payoff of the first state of nature times the probability of that happening, plus the payoff of the second state of nature times the probability of that happening, blah, 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 until you get the payoff of the last state of nature and the probability of that happening. And then you pick the one with the largest payoff when you're all done. So let's take a look at an example there. So here's a large plant, small plant, and it's basically the Laplace or Hurwicz when alpha equals 0.5 in this case. So you have 200, you're taking the average again, because weighting things by 50-50 is basically taking the average. So we get 10,000, we get 40,000, we get 0. If you're going to pick the max of those, you're going to do the small plant. So it's exactly the same table. Expected value of perfect information. Well, do you have perfect information? EVPI, expected value of perfect information, takes the expected value with perfect information minus the maximum EMV. So the EVPI, best payoff for the first state of nature, probability of it happening, best payoff for the second state of nature and the probability of that happening, best payoff for the last state of nature and the probability of that happening. So you're not picking things from different rows. The best answer in each row times the probability of that happening. For each state of nature, for each column, you're picking the best. I'm sorry. So suppose scientific marketing offers an analysis that will provide certainty about the market conditions. Additional information will cost, there is scientific marketing where they have economists on their staff. They will sell you their report for $65,000 should Thompson Lumber purchase the information. Well, here, let's look at this. Here's the original table right here. 200 minus 180, 100 minus 20, 0, 0. Here's your EMV, 50-50. Now, what's the maximum of each column? Well, here it's 200. Here it's 0. Remember, when we're maximizing negative numbers, we pick the least negative number, which in this case is 0. I use the 50-50, I get $100,000. If I had perfect information, my payoff would be $100,000 if I did this over and over again. They're charging $60,000, so it might be worth it. 100 minus 40, or basically, which is the other decision, is 60. So the maximum Thompson should pay for the additional information is $60,000, not 65. You could probably negotiate with that scientific company to have them knock $5,000 off the price. They might go for it, or they might say, sorry, this is our price. How valid, how accurate is this? I don't know. It's as accurate as these numbers and these probabilities are. Again, you could be convoluting the answer, getting too far away from some gross assumptions, which basically this chart is made from. I'm not saying don't do it. I'm saying be cautious when you do. So therefore, Thompson should not pay $65,000 for the information. Expected opportunity loss is a cost of not picking the best solution. First, construct an opportunity loss table. Then, for each alternative, multiply the opportunity loss by the probability of that loss for each possible outcome and add these together. The minimum EOL will always result in the same decision as the maximum EMV. So why use it? I'd use the EMV, at least it's, to me, more straightforward. Minimum EOL will always equal EVPI. So there you go. Expected loss. And you get the 60,000 again. Sensitivity analysis examines how the decision might change with different input data. In this case, we're looking at the probabilities of a favorable and unfavorable market. Play around with them, see where it goes. So you can come up with your calculations and have a line for each one. If you have 200p minus 180 times 1 minus p, do the math and come up with a line. 380p minus 180. In this case, you get 120p minus 20,000. And here you just get 0. Well, now if you graph these lines, it tells you where the breakpoints are. For if you think the probability of a favorable market is going to be above 61.5%, you would always pick the large plant. If it's between 16.7 or basically 17% and 61.5%, you're going to pick a small plant. If the probability of a favorable market is under 17%, you probably want to also do nothing, because you have least loss, or a small plant, which you have least loss, or the do nothing, which is 0. Excuse me, I'm sorry. You would do the do nothing, which is 0. So do nothing range, small plant range, big plant range. And you just see where your breakpoints are. And you can debate all you want about the favorable market conditions or unfavorable market conditions. Who has a final say on that? Oftentimes the CEO. Oh, I'm certain we're going to have a favorable market because he wants to construct a big plant, or she wants to construct a big plant, and there you have it. You've got your... You're no longer under certainty, you're under risk because a knowledgeable chief executive has told you so. Not that he knows any better or she knows any better. Okay, so sensitivity analysis, do nothing, and EMV of small plant. So that's point 1, point 2. I mean, that's what sensitivity analysis is. I'm not going to make you do it, but I think you should at least look at this kind of thing to make the determination. Again, if it's less than 16.7%, do nothing. If it's between 16.7 and 61.5, construct small. If the probability of a favorable market is greater than 61.5%, construct a large plan. Now, when we look at, here's the formulas in the QM model. And when you put the numbers in, and I'll probably post another video of probably solving the Thompson problem in this case. And it gives you all the answers. It really gives you all the answers, whichever model you want to use. So you don't have to model it differently. There's a probability play. So here they put 0.5, 0.5. So that's Hurwicz. You can also put a Hurwicz coefficient here. So this will give you Laplace. This will give you, it's under risk because we know what the risk is. Here's the payoffs that you have. It gives you your EMV. So if you want your maximum EMV, pick the small plant. If you're doing the minimum and you want the maximum of that, you're going to choose this alternative, which is do nothing, which is the Minimax. If you want the Maximax, you're going to pick the max of this column, which is 200. If you're going to do the Hurwicz, you pick the max of this column, which is 124, which is also a large plant. If you're going to do the regret table, here's your regret table with your variables and everything. If you do the expected or you do the maximum, in this case you're going to pick, it gives you the minimum in each case. In both cases you're going to pick a small plant. And so you could answer all the questions depending on which model you're asked to do by using this QM model. And it tells you how many states of nature does it have, and you've got to put that in, and how many alternatives you have, you put that in, and it gives you a table like this, and you fill out all these labels, and you fill out these numbers, and the ones that are shaded is what you fill out, and then it gives you all the unshaded numbers. Hurwicz numbers shaded, so you can put that in there. And basically one table will give you all the answers. I kind of like looking at all the answers myself. And then I can answer, well, if we do this. And then guess what? Let's look at this. EMV, small plant. So that's one for small plant. Minimax, do nothing. That's one for do nothing. Maximax, large plant. That's one for each. So I've got one for each now. And then when I go to Hurwicz, it says large plants. So it's 2 for large plants. And then if I go down here, I get 2 for small plant. So small plant wins the majority of the decision-making options. I would go with the small plant. But that's the difference between, I'm somewhere between being risk averse and a risk taker. And I know we have to do something. So let's make the small plant with, like I said before, room for expansion. So we're going to stop here because we're not doing decision trees. And I thank you, and I hope this presentation helps.